Okay, cool. Thank you. So, hey everyone, my name is Florin. I work at JetBrains as a developer advocate. And normally I talk about IDEs, Go, modern web development with Golang, microservices, and so on. So, instead of doing that today, I would like to share my experience when building an FM radio transmitter with Go. First of all, I should have said that thank you for having me here today, and thank you to the organizers for the conference. From what Shenya tells me, it's a really lovely one. So sorry I couldn't be there in person, but who knows, maybe next year. That being said, let's move on with our presentation. Why have I built this? Well, because I wanted to do something that is fun. I also wanted to do something that is not the standard microservices talk. So I got bored of doing microservices. And I also wanted to learn something new because, yes, building APIs in Go is fun. Building high performance systems is fun, but, well, maybe there's something out there beyond that. Another thing is that I wanted to do something useful for my car. And when I say that is because I started automating my home first, and you can actually find a talk about that from last year. But then I was like, okay, maybe I should do something about my car. And what could I do useful that I can program for my car? Well, not the self-navigation thing, as all the cool startups are doing, but rather just provide TMC data for the car's navigation. So why is that? Now, I bought this shiny new car, right? And it has an awesome display and navigation and so on, but I do not have the capability of using it fully because without the TMC data or the traffic message channel, I cannot tell my car's navigation that it will encounter any problems on the road. For example, there's no road closure information or traffic jams or anything like that. So without that, I cannot use it fully. I have to use either Waze or some other application like, I don't know, Android Audio or Apple CarPlay. And I definitely don't want that. I want to use my car's navigation. So enter the hackery. First thing and foremost was how do I broadcast that information? And turns out that TMC is part of the RDS or radio data system. That is also known as RBDS in United States. And what it means is that it's a form of transmitting additional data from FM radio stations through the radio waves, right? If I would look at my car's navigation, I could see that this is what kind of radio data system information I can get. I can get, for example, the station name that I'm listening to. This would be the message that they want to send. And I get to see station names and so on my onboard navigation. Traffic message channel, it's basically another data that is sent over the radio waves. So, okay, if I can make a radio station first, then I can hack my way through getting the traffic message channel. Unfortunately, today we'll stop just before transmitting the traffic message channel, and who knows, maybe at a later talk we'll see if that worked out or not. So let's do a short introduction to radio waves to see how we achieved transmitting radio after all. So make ourselves some radio pirates. For this one specifically, I used high-frequency radio waves with frequency modulation encoding to transmit data. And if that is a mouthful of physics terms, let's familiarize ourselves with that. So let's make a short introduction. Radio waves are basically a form of electromagnetic radiation that happens either in natural conditions or artificial. Natural conditions for radio waves are when, for example, the lightning appears, or stars, or any galaxies and other astronomical bodies are emitting that radio wave. Artificial waves are, for example, satellites or, I don't know, 5G phones. Well, 3G phones too, but 5G is modern. And so on. So it's basically what we as humans generate in terms of radio waves. Radio waves have three properties. They have speed, so that is measured as the speed of light when traveling in vacuum, but radio waves are impacted by the medium they are traveling. For example, if they pass through atmosphere, they get slowed down as the light gets slowed down too. Or if they pass through concrete walls, buildings, trees, humans, and so on. They have a length or a wavelength. So if you've heard of that, it's basically the distance between one peak of the wave and the next peak of the wave. And finally, they have a frequency. So that frequency basically measures how fast a peak happens for that wave. So the faster the frequency of the radio wave, the smaller the distance between the peaks becomes. And this is a bit helpful to understand how we can send data through it. If you want a graph of how a radio wave works, you can find one that I found on Wikipedia, but basically it looks like this. This would be in blue above the top here, our radio wave. This would be one peak. This would be the next one. And the distance between them would be the wavelength. The frequency at which a peak appears on the same spot, let's say, is, well, the frequency of the wave. And the speed is basically the speed at which the wave travels. So let's move on and see how we can broadcast data using radio waves. We have the amplitude modulation way, so that we'll cover in a second. We'll have the frequency modulation, which is what's interesting for us. And we have a few other digital transmissions that we can do, such as the digital audio broadcast, HD radio, and a few other formats, but we won't cover those today. Amplitude modulation, or AM, is the form of modulation which varies the signal strength or amplitude based on the data that's being transmitted, such as an audio signal. So, for example, if we want to transmit this signal here from the information signal, and we have our carrier wave, which looks pretty standard, right? That would be the radio wave, let's say. The modulated version, so the one that actually transmits data, would look like this. So we vary how big the peaks are so that we can shape our information that we want to send. Now, this was one of the first forms of transmission, but it was later discovered that is not as efficient or useful as the frequency modulation. What is frequency modulation? Frequency modulation varies the instantaneous frequency of the wave of the carrier wave to encode the data. And it looks a bit like this. So it's a bit more complicated to visualize. But basically, if you have a signal here and you have your carrier wave, so it looks the same, you basically would have to try and see how that looks like in this diagram. It's not the best one that I have, but hopefully it should give you a rough idea of how an FM signal looks like. Okay, let's talk a bit about other broadcasting formats, just to touch them a bit. They are digital audio broadcast, or DAB and DAB+, and they've been around since mid-90s. It's still not super widely used. It's all in most of the countries on Earth, but there are very few stations usually that use this format. And in places where that format does not appear, it's because maybe they are using something like HD radio. HD radio, of course, is present in the US, because why not go with a different standard than the rest of the world, as well as Canada, Mexico, and a few other places. So this one has been around since 2002, and, well, the same story as with DAB. still not widely used. I think enough with the physics lessons. This is not a physics 101, it's a Go conference. So let's go with a bit of making waves. This is how the system looks like. So if you're curious and you can't wait anymore to see how the system got created, that's what it is. And I'll explain all the components in a minute. So we are using a Raspberry Pi, which is a single board computer of the size of a credit card. That means that it's small enough that we can carry around or put it somewhere that doesn't have to take a lot of space. It's also very battery efficient and so on. So it appeared in 2012, and it first was meant as an educational tool for teaching people, kids and people in under technologized areas to have access to computers, basically, to learn how to program, to learn how to use computers and so on. It also, however, got traction in the hobby market, and that's why it sold over 30 million devices, and that's the figures according to last year. I'm sure there's a lot more sold now because they released a bunch of those devices. They can be used in everything. So they can use from simple apps that blink an LED all the way to robotics applications. And since they released a few of these devices, I'm going to just tackle the last one, give you some specs for it. It supports a quad-core ARM-based system on a chip. And to put it in another way, it uses a CPU that you can have that has a similarity with the chip that your mobile phone is using. So most likely if you run an Android, for example, or an iPhone, those use an ARM-based system on a chip too. It uses up to 8 gigabytes, so it has plenty of memory to go around and do tasks. Mine has 4 gigabytes, for example. And it can output video on a display up to 4K, so Ultra HD 60 Hertz, or 2 displays of 4K 30 Hertz. That is pretty powerful for such a small machine, right? This is how it looks like when it's not in a case. And you have here the system on a chip itself, the memory, some controller, the Ethernet controller, which supports 1 gigabyte a second, USB 3, USB 2, audio jack, camera connector, display connector, power, micro HDMI, and of course you have some GPIO so that you can connect components to it. Now, I said something about a case, and you may have noticed the thermal pads on those chips. That's because it kind of runs a bit hot, so you have to cool it down somehow. Let's move to the transmission part. So how do we transmit data? We are using the Adafruit SI4713 transmitter, which uses the Silicon Lab chip with the same name. It can send RDS and RBDS data, and that is exactly what I need to send to my car, right? So it's the information channel that I was interested in having support, and it means that I can do what hackery I need using it. It supports the transmission of up to 10 meters or 30 freedom units, and that means that it doesn't have to be like, I'm not gonna mess up with anyone else's radios. However, check the laws in your country to make sure that you don't have any issues. And it supports a line-in method for getting the audio data, which made things easier, as well as receiving commands over I2C. So that makes things easy to program and find examples on how to interact with the chip. Not only that, but drivers are available in C and Python. And up until I started working on this, I couldn't find any drivers in Go. So that's why I had to create my own drivers. Now, that also meant I have to port them in Go. So how did I port them? Well, let's see first how the transmitter itself looks like. So this would be the audio in that you can use, or you can use these pins to send audio signal straight to it. This is the chip itself, and this is the antenna that it's a bit longer, but it has a sort of an antenna because it needs to transmit. And yeah, please ignore the soldering job I did myself here. So yeah, I'm not a good pro at this yet. So how did I write the device drivers? Well, I wrote the device drivers using GoBot. And if you're not familiar with this, GoBot is a framework that allows you to write robots, drones, and other IoT devices software for. So most likely you'll find it as a very useful project. For me, it certainly was. It's stable. It has been around for quite a few years, 6 or 7 if I'm correct. And it supports a bunch of platforms to run on. So if you look at the documentation page, it supports over 30 different platforms to run Go code on. So that is quite cool. It also supports a lot of devices out of the box. So these devices would be devices like the FM radio, for example. But as I said, it did not have any support for this chip itself. So I could use one of the examples that I had for 19 GPIO devices, or maybe one of the 5 AIO devices, or maybe it was the 9 serial peripheral interfaces devices that I had, SPI ones. But more useful were the 24 I2C devices, I2 devices, which were similar to the chip that I had. So because the documentation and the drivers that were available were super useful as a starting point, I started to hack around, and it maybe took about a day or so to complete porting the driver itself. This is how the page looks like for the GoBot project. And I'll give you a second if you want to admire the Gopher here. It's an awesome project, and I highly recommend it. So yeah, just go and visit the page whenever you can. Okay, so I think I've shown you enough slides. Let me try to show you some code and explain how all of this came together. So what I have here is the code that stands behind the radio transmitter sample that I have for today. And off the bat, you probably noticed that I'm using like an FM station name. I have an RDS message that I'm putting out here. I'm initializing the Raspberry Pi platform. And then I am using a radio configuration for the device itself. This configuration has a transmission frequency. It is a 95.5 megahertz. So when you read that 9550, it would be like this, but it doesn't support floats. So it's going to be like that. It also supports a transmission power setting. So it's a weird one, but trust me, that's a good number. We do want to send RDS, and we have a program name for the RDS station, or better said, a program ID. And then we initialize the chip driver itself. I'm also initializing a LCD, a small LCD screen, just to display some information on it, and actually ensure that this is a live demo. Could be a recording, you never know. And finally, we initialize GoBot, and we tell it, hey, this is the name of our robot. I'm using the Raspberry Pi connection. I'm using these devices, radio and LCD. I start, or if I fail, I'm logging the error. There's a worker function that you may have noticed. In this worker function, we display some messages on the LCD. We get to display, we get to actually set the message that goes to RDS. So this is part of being able to transmit RDS data. Again, it's just an example, so there's full of log fatal error and so on. And then every second we basically loop through the radio, and we also do, I don't know, let's say a display for the date and time on the display of the LCD. Okay, let's jump a bit into this because it was quite a lot to unpack here. So let's jump into the new driver. When we jump into here, we see that we first and foremost initialize our display driver here. There's not much interesting for this one, so it is pretty simple. If we jump into our FM transmitter, however, there's a lot more data to use. So first and foremost, we have to validate it. Validation takes place, good old hand validation method. And we check for a few things like having a log function, being in debug mode, what's the reset pin, maybe doing some defaults if we don't have a reset pin, and so on. So there's a few things that happen here. Standard things, I would say. We then initialize the FM driver, and we say, okay, give me a default name for the driver, give me a default name for this, give me a configuration, set the address to the device, and then apply the configuration that we have. So not many useful things here. What happens next? So under the hood, if I look here, there's not an explicit start, it's just the one that I have here. So let's look at our device driver here. Our driver is based on a similar structure with other I2C drivers. And basically, we have a I2C connection, one connector, some configuration, and our internal configuration here. As you can see, we also implement some interfaces. For example, I'm implementing the config interface here, which allows you to have methods with bus, for example, or get the bus itself, or set the address or get the address for the device. And that's not really the interesting ones. The interesting one would be the driver itself. So when I said that I'm using the driver interface, I also meant that I have a start, a halt, and a connection method. Connection method is fairly simple in our case, but the start and halt ones may be interesting to observe. Once you're able to start the device and halt it, then pretty much you can do any other communication. So if you pass that point where you say start and connected the device and it doesn't burn up, then you're good to go to do other things. In my case, I was fortunate enough. It took 1 day to write the code and 2 more days to convince myself that, okay, probably I did the right thing. It's not going to burn up and spend another $20 on it. So that was the moment when I was like, should I start this or not? Let's go with the start method first. So in the start method, we do ensure once again that we have some specific values here, just to be sure that we did not mess up anything. And then we get our connection from I2C connector. With that connection, we set it on the bus, and then we say begin. And this is where the magic happens, so to speak. Begin, basically, we'll initialize the device itself. If I go into the reset function here, I get to have a digital writer, which allows me to say, okay, let me put the device into the reset state. How did I know how to do all of this? Well, I had the C drivers and Python drivers, and I had the manual to read through. Because despite of all those 2 drivers, sometimes the manual for the device itself was useful. And that's how we do it, basically. We say write the high value, so 1 or 0, on the reset pin, and that tells the device to reinitialize itself. And that's about it. If we go back into power up, then we have a few more interesting things, and I will give you a demo too. So let's speed up a bit through this. So I have a send command. Sending command was fairly straightforward. There's a connection write, which writes a command, and then we can also wait for that, unless it's the power down command, which we then don't need to wait for. But basically, we can read and write to a connection, and if you notice, this would be the the write interface, and this allows us to read from it. So it's all using standard Go interfaces. Setting a property on the device itself, again, super easy. Set property device on the device just takes one of these commands and then it configures it and then sends it to the device itself. So that was, again, fairly straightforward to do. And finally, there's a lot of documentation here, but I think probably what you want the most is to see, okay, does this actually work? And for that, let me bring up the AirSpy. I'm not sure how the demo will fare, so let me connect to the Raspberry Pi first. If I don't have a typo. Okay, can you all see the screen here? And I hope the answer is yes, because I can't see you or hear you. So I have the go run command, and to make it a bit more fun, let me see if I can. Where are you all? Okay, can you see the camera?
Yes.
Okay, cool. So this would be my desk, and sorry it's a bit messy, but this is the device. This is the Raspberry Pi, so it's powered up and everything. And this is my phone. Now, if I unlock my phone and start playing some music on it, like this one from YouTube. So this is all free music. I don't know how to hold the camera for the reflections. It's too shiny. So now I'm playing something on my phone, right? And you can't hear anything. Let's do a go run. Ooh. See, it's actually a live demo. First time around. And now let's start this one.
Oh, yeah.
And I know you
Cool.
you don't know. Let me see if I can. I don't know if you can hear anything.
No, nothing.
So yeah, basically it kind of works. I did try my best. At least the LCD screen works, right?
Yeah, I believe you.
You'll have to believe me. Well, sorry. I mean, like, I kind of wanted to do this live, but there's a tiny thing in my way. So anyway, let's finish off the presentation. And why did I want to do all of this? And it turns out it kind of works. You'll have to trust me on that one. So why did I want to do this? Because I was bored of writing servers and stuff, and it kind of worked out fine-ish. Well, there's a panic that I need to solve apparently. GoBot is a lovely project, and I highly encourage you to check it out. I can't thank the authors enough for it, and that made things a lot easy. And you don't have to worry if you don't know C or Python. I still don't know C or Python, but I was able to somehow make this work in Go based on those drivers. So that was fun. And yeah, well, now all my neighbors can enjoy what music I'm listening to. So that has an added bonus. If you want to get the components list, I've put together a list of all the things that I used. You don't necessarily have to use a Raspberry Pi with 8 gigabytes, but if you also want to get more power and, I don't know, run our IDE on it or run some other tools on that, like Kubernetes maybe, that's a very good platform to experiment with, and it's rather cheap. You also have like literally all the things that I used here, and there are some optional components that you can use too, like the soldering iron, and there's like the small LCD that I had and so on. And of course, there's an FM receiver that I couldn't show. Actually, let me unplug it. So this one is the FM receiver on the computer. I hope you can see it on camera.
Yes. Yes.
Yeah, so that one actually is fun if you want to receive FM radio on your computer. That was the thing. If you have any questions, I'm not sure if we still have enough time for them. Sorry, I tried to speed up through it as much as I could.
Yeah, because of the running out of time, so we will have one question for the Q&A part. 我们开放一个问题，就是 Q&A， 然后可以讲中文，我们这边有专业人士翻译。就是有没有人对于刚刚的演讲有任何问题想要询问的？没有吗？
我觉得我们叫他把那个他的
麦克风
有吗？好，那你可以打开你的麦克风吗？你如果可以讲英文，可以讲中文都可以。
Hello. I want to know how many time do you spend on this project? Very curious about this.
So actually, sorry, I think there's a bit of delay. So how many hours did I spend on this project, right?
Yes.
Okay, so it took about a day and a half to take the C and Python sources and port them to Go. So it was a literal one-to-one translation, and then I had to make it a bit more Go-like. And then it took about 2 days to convince myself that I did the right thing and I can power up the device without burning the device. But all in all, it took about a week to do. It maybe took a bit longer because I did, like I said, I was a bit scared of actually burning $20 because that's how much this one, the radio transmitter is. And I was like, I'm not sure, let me review the code. But it's not very hard to port these devices to Go. GoBot makes things a lot easy. And in this case, I also had really good driver examples from Adafruit. And I also had very good information on the, how do you call it, from the manual for the device. So yeah, it's not that much time to spend on. I will, actually, the code is open source now, but I will merge it to GoBot. So there's a pull request that I will send out later on today to the GoBot repository. And you can review it.
Okay, thank you, Florin.
Cool. Thank you so much for having me here today. I do hope you enjoyed the presentation. And once again, thanks to the organizer for inviting me. So enjoy the conference. See you all.